If you are analyzing DNA, this is your final stop. Under ultraviolet light, an invisible biological sample becomes a perfectly organized, glowing barcode. This diagram outlines the underlying principle of gel electrophoresis. Because molecules like DNA have a negatively charged phosphate backbone, we can use an electric field to pull them through a porous matrix to separate them based on their size and charge. Before you touch a pipette, ensure you have your casting tray, a power supply, and an electrophoresis tank ready on the bench. You also must put on fresh nitrile gloves and UV-blocking safety glasses. Setting up this equipment correctly is the mandatory first step for nearly all genetic screening, forensic analysis, and gene cloning. Without a clean run here, you have no downstream data to analyze. Step 1 is building the matrix itself. You start by weighing out dry agarose powder, mixing it with a conductive liquid buffer, and heating the solution until it melts completely into a boiling, clear liquid. Once it cools slightly, you slowly pour that mixture into a sealed casting tray. You want a smooth, steady pour to avoid trapping any air bubbles inside the liquid. This diagram illustrates the next critical step, placing the comb. You insert this directly into the liquid tray. The teeth of the comb create small, uniform pockets, or wells, where you will eventually load your samples. Over the next 30 to 45 minutes, the hot liquid physically cross-links into a solid gel, turning slightly opaque as it sets. Do not rush this step. If you pull the comb out before the gel is completely solidified, the fragile walls of your wells will collapse, destroying the entire cast. A perfectly cured agarose gel acts as a microscopic three-dimensional sieve. Its structural uniformity ensures that your DNA fragments will encounter consistent physical resistance, which is the only way to achieve accurate separation. With the gel solid and the comb carefully removed, place the tray into the central electrophoresis tank. Then fill the tank with buffer until the gel block is completely submerged. Because DNA is clear, we mix the samples with a heavy blue loading dye. This gives us a visual tracking marker, and more importantly, it adds physical weight to the sample. To load a sample, lower your micropipette tip until it hovers just inside the upper edge of the submerged well. As you slowly depress the plunger, that extra weight allows the dense blue sample to sink to the bottom of the pocket on its own. You must keep your hand steady. Do not push the pipette tip deep into the well or let it touch the bottom. If the tip punctures the agarose matrix, your sample will leak straight through the bottom of the gel into the surrounding buffer. When you read the results later, that lane will be entirely blank. The success of the entire run relies on the precise execution of this single physical action. Seating the sample perfectly inside the well guarantees that all the DNA enters the gel matrix at the exact same time. Secure the lid and connect the cables. Place the black negative lead near the wells and the red positive lead at the far end. Remember, run to red. Because DNA is negatively charged, it repels from the black and travels toward the red pole. After you turn on the power supply, check the tank to visually confirm the system is working. You will see bubbles of hydrogen and oxygen gas fizzing off the submerged platinum wires. Be careful with your settings. If the electrical voltage is set too high, the system generates excess heat, which can literally melt the agarose and permanently destroy the physical structure of your sample. You also need to monitor the clock. If you walk away and leave the current running for too long, the DNA fragments will migrate straight off the far end of the gel and be lost into the buffer tank. Running electrophoresis is always a deliberate balancing act. You are applying a specific electrical force against the physical resistance of the gel over an exact window of time. When the runtime is complete, turn off the power. Slide the fragile wet gel out of the tray and transfer it to your UV transilluminator, making sure your eye protection is securely on. Activate the UV source in the dark. The stain binds directly to the DNA, causing the hidden fragments to fluoresce brightly against the dark glass. This diagram shows the logic behind the resulting band pattern. The gel matrix acts like a physical obstacle course. Larger DNA fragments get tangled near the top wells, while smaller, compact fragments slip through the pores and migrate further down. This troubleshooting table helps diagnose experimental errors. Seeing no bands usually means your DNA concentration was too low, or samples ran off the gel's edge. Smeared or unseparated bands indicate you likely applied too much voltage or mixed the wrong agarose percentage. By perfectly casting the matrix, maintaining exact pipetting technique, and carefully controlling the electrical current, you force a complex biological mixture to reveal its structure, providing you with verifiable, actionable data.